Welcome. In this session, we'll explore how we can computationally model a simple artificial neuron. This begins with the weighted sum that we described in the previous session, which is the inputs are the voltages on the dendrites, and the weights, which we'll originally describe as values m and later we'll describe as values w, are a modulation of these inputs, and these are the memory that the cell has and develops, and these are what we are going to want to learn. The bias, which is in cell terms beta and in linear algebra b, it represents the threshold that we see at the axon hillock of our simple neuron, and the output occurs when the summed voltage exceeds the bias. So we can write this in two ways. One way is we can say that each of the original inputs is multiplied by a weight, and the cell fires when this is greater than or equal to the threshold in the axon hillock. Another way to put this is to say that when we multiply the inputs by the weights and then add a value, a bias value, then when that's greater than or equal to 0, the cell is going to fire. So in this case, we see that b equals minus beta, which is a very typical way to do things in linear algebra. There's also an activation function that we'll introduce later on in this session. So the data comes from the top, and because we use observations. So it starts with our data, gets multiplied by the weights, gets added up as a sum. That's what we call a linear response. And then in addition, there's an activation that produces, depending on how we're working with it, it's either a function value or sometimes we'll refer to that as the score of this data. Now, when we actually go to implement this, we don't do this one set of multiplications and then add a scalar. What we do is we augment the data. So we take our original data, augment it with a 1. That's our new observation for our artificial neuron. We take the original weight and the original value b, the bias scalar, and we augment those, and now this is the weight vector, and this is what we're going to learn, and this is what a cell effectively learns by learning its weights and its axon hillock bias. So the weighted sum for observation I will represent this as u sub I, and that is just the observation times the weights, which is a homogeneous way of representing this inhomogeneous equation. So the neuron will fire if and only if this linear response is greater than or equal to 0. Let's also observe that there are labels along with the data, and the user has to provide a label for each data vector or observation. The terminology varies in neural networks, and we have to remember that this label is binary. It's either 0 or 1. So for a single neuron with augmented data, what we do, we augment it with 1, and now our flow is very similar, and sometimes we'll just represent this as a single circle, and inside that circle is happening the summation to get the linear response and then the activation function, and then the result is this output. And traditionally this output is in the range of 0 to 1. There are some methods that produce values that are outside of 0 and 1.